So welcome to today's webinar, which is the last event of the Nexus Horizon Europe project. The Nexus Horizon Europe project is a 3-year project. I'll give you a very, very brief presentation. But today we wanted to discuss the results of the project and what that means in terms of policy levers or policy opportunities or barriers that we could need to go further in deployment. We have 3 speakers with us today. Maria Getsiou from the European Commission, who is Senior Expert in Renewable Energy Sources, who is going to take us through a bit of the European policy environment. We have Perrine Carroy, who is our project coordinator from the CEA, who will run us through the key technical highlights of the project. And Nouha Gazbour from the CEA as well, who will run us through the results of the multi-criteria dimension analysis and what this means in terms of policy levers for scale-up and deployment. Now, it's completely by unintentional that our panel is mostly CEA today. We have a very wide-ranging consortium with partners across Europe, including for example, Oxford University, SALD. We have University of Valencia in Spain. I think I can't remember whether it's NL is the actual partner. We had a few administrative changes, but we also have URAC, KIT, and unfortunately Norsan, who had to leave the consortium. I'm sure you've all followed the news about the developments in Norway. But so we have quite a wide consortium. We've been working together for 3 years now on this project that has just finished. And as a very brief overview, Nexus was a project, crystal silicon perovskite tandems project with a very clear focus on developing sustainable tandems with a range of work packages running from developing perovskite absorbers layers using solvent-free sustainable methodologies, which means it's a little bit different to many of the other perovskite research projects that are happening at the moment. Developing these deposition technologies for low environmental impact manufacturing, specific target power conversion efficiencies, looking at very exacting bill of materials for different types of applications. We also ran through looking at what could be the priority or most interesting markets for crystal silicon tandems coming out of perovskite, scalability and proof of concept equipment sets for the different processing steps in the production. One of the added values of our project was having organizations that are very close to manufacturing. We did outdoor durability testing, indoor durability testing. Some of you may have seen the results that have been presented in the different research conferences over the past couple of years. And finally, an overarching task at the end is a multi-criteria dimension analysis that combines all our investigations into the environmental sustainability, the possibilities of recycling, the life cycle costing, the social impacts, and the technical results, and looking at what does this mean in terms of overall impact? What are the different levers that comes out of this? It's a very brief description of the Nexus project. I will hand over to Perrine, who will run through the main technical results with you. Thank you, Perrine. And just before I forget, we are recording, so if you don't want to be seen, please cut your cameras.
So then I go first, Melodie, and then we give the...
No, Maria first, sorry.
Maria.
I think it might be more interesting if we have our guest first. It's what I put into the agenda. My apologies.
Okay. Thank you very much. Thank you very much for the introduction. So I'm Maria Getsiou. I'm working for the European Commission's Director General for Research and Innovation. So I will give an overview of the support that we give in terms of research and innovation to perovskite PV. So perovskite PV has been a technology that is booming in terms of support, actually the last year's support in R&D. And this is, of course, very much understandable because of the steep increase in results that have been demonstrated in perovskite PV. So there has been an increase in the efficiency, which cannot be matched by any other technology in the last years. And of course, for many advantages that the PV technology offers. There are, of course, many challenges that still need to be resolved and responded to in order for the technology to move from the lab to the markets. And yeah, these are partially, some of them have been mentioned before. So in terms of sustainability, in terms of lifetime, of manufacturing capacity or easy manufacturing, which is linked also to the lifetime and to the cost of the final product, etc., etc. So the last years, we have concentrated efforts in terms of research and innovation in these challenges, and we have concentrated also budgets on these challenges. In Horizon Europe only, we have devoted, I think, more or less under the program on climate, energy and transport, around 90 million on around 17 projects on perovskites. And I think another equivalent amount perhaps is being dedicated from other parts of the framework program, from mono-beneficiary programs which are devoted to the EIT, to the ERC, to Marie Curie actions, to programs or projects for the development of materials and so on. So there is a huge effort from the side of the European Commission to dedicate an important financing on the research of PV, of perovskite PV. And this is explained by the fact that Europe would like to have a competitive advantage, at least, or to create a competitive advantage in the technology that would allow manufacturing capacities in this specific technology or combination, tandem technology between perovskites and crystalline silicon PV, and then gaining a part of the market. Apart from, research cannot do that by itself alone. Research creates perhaps a competitive advantage, but at the same time, in order to have competitiveness, and this is the buzzword that we use lately in the European Commission jargon, you need to have other market and industrial initiatives in order to be able to translate this competitive advantage into competitiveness. But in terms of market, the European Commission recently, with NENZIA, so the Net Zero Industry Act, supports or tries to support manufacturing of PV because it has set a specific target for creating resilience in clean tech technologies. And specifically in photovoltaics, we are very much dependent on Chinese imports. And therefore, in order to create resilience in the market, first of all, we are requiring that certain auctions, for example, public auctions, set resilience criteria that can be also made in Europe, depending on the member state where these auctions take place. These are the market measures, but also in terms of manufacturing, there are certain projects which are called net zero projects or net zero projects of strategic importance, where member states can support or give direct aid, which normally cannot be given, in terms of capex and sometimes of opex in these projects. And it can be manufacturing projects on PV. So all these are not dedicated specifically to perovskite, but perovskites being a technology which is innovative and a technology for which all over the world now there is a course on who is going to come first with manufacturing capacity either on perovskites or on tandem perovskites with PV. And there is a bet actually who's going to do it first. So this is why we are talking about manufacturing of innovative technologies, including perovskites in Europe. So in terms of support as well, apart from ENZIA, there is the Clean Industrial Deal State Aid Framework, the CSAF, that has been recently introduced, that allows member states also to support manufacturing of innovative technologies, including PV, innovative PV technologies in member states. Now, if we come back to research and innovation, as I said before, we have increased financing, we increased funding of perovskite PV in the last framework program, and we expect as well from projects to deliver upon what they have promised. So to deliver, to reach their deliverables and to progress. Another thing that I would like to mention is that because perhaps efforts are being split and a more intensive cooperation between projects or between European institutes on PV research might be needed. So if you join forces in specific aspects or specific challenges of PV, of perovskite PV research, or divide work according to specialization, or grouping the challenges and working some institutions on challenge A, other institutions or challenge B, etc., that might help as well in order to progress faster than spreading actually the research efforts all over all of the challenges and all over all institutions. I think, and because your presentation is going to be about sustainability, and one of the challenges that perovskite PV is facing is sustainability, with the inclusion of PB lead, but also on how actually this is handled in terms of manufacturing and then in terms of the end of life treatment of modules that contain lead. We would be eager to see what the project has done in these terms. But in general terms, because sustainability, it's not only environmental, the handling or how we manage the environmental risks or the other risks of the project itself, but in terms of a general or of a global footprint, CO2 footprint of the final product in conjunction with the lifetime and with the avoided CO2 emissions that the product might have. I think all these aspects together would allow perovskite PV to claim that they can provide that they are a sustainable, environmentally sustainable technology that can compete with other technologies offering the same result, offering the same product. So I am eager to see what the project has done on these aspects, but also how the project has tackled some of the challenges, some of the specific challenges for perovskite technology. So this is from my part in the introduction, and thank you very much for having invited me.
Thank you, Maria. Thank you, Maria. I'm glad to hear that one of the focal points on the environmental impact of Nexus, which was managing lead is very interesting for the European Commission. It means we were looking at the right things. I'll hand over to Perrine Carroy, who is our project coordinator, who will now give you a run through on the technical results of our project before we hand off to Nouha. Perrine?
Yes. Hi, everyone. Thank you, Melodie. Thank you, Maria, as well, for your introduction. I will share my screen and give you some results on the technological side. So Melodie has already presented a little bit our consortium, and yes, so Nexus, the topic of the project was really perovskite on silicon tandem devices, and with a special focus on trying to make this technology scalable, industrially viable, and sustainable. So, of course, we had to focus on experts really on the technology, really on developing processes that are scalable and sustainable. We had to demonstrate or that we can ensure long-term stability at the module level, which choosing an appropriate bit of material for the module, and also, of course, stressing the modules in real-life conditions. And there was a huge work really in anticipating the future deployment of the technology, with a lot of assessment reports to demonstrate that it can be scalable, economically viable, to assess its environmental impact and its social acceptance, proving the circularity as well, with proof of concept process as well, and with the overall goal to establish policy guidelines for the deployment of this technology, which is of course the topic today, and which will be the main topic of the next presentation by Nouha. And for the current presentation, we will have a closer look to what we've done really on the technological side to try to make this technology scalable and sustainable. So when we have a look at most perovskite on silicon tandem devices that are published in the literature, for example, the perovskite top cell, it relies on a solution process which uses epoxy solvents, and it's also non-scalable because it's done by spin coating, so it only can be done on a single small pieces of sample. And our choice to address this point in Nexus was to work on vacuum-based processes like co-evaporation, sequential evaporation, and also hybrid, where you have a vacuum process followed by a solution process, but only using more environmental friendly solvents. On the silicon bottom cell side, so what most, the vast majority of the results, they rely on thick flow zone wafers, which are very, very expensive. You can absolutely forget of having an industrial technology based on these wafers. And well, as I was saying, in Nexus, we have done some life cycle analysis, and already if you have a look on the impact of the technology at the module level on climate change, so on CO2 emissions, the silicon wafers has it's the main contributor to CO2 emission, and in the cases that were studied in the project, so even the baseline was already on a wafer with a Shogradski technology, 170 micrometers, but sourced from China, and with the optimized scenario, then it was sourced from Norway, which is unfortunately not a possibility anymore, and this strongly reduced the CO2 emission. So if you already only look at this, that only on thinner wafers with the Shogradski process, it's already done in environmental country, let's say, it's already still the main contributor to CO2 emissions. So there's no way that we can have a sustainable technology relying on thick float zone wafers. So this is why this is the first step that you have to make this technology more at the same time sustainable, to reduce CO2 emission and to make it industrially viable, is to switch to Shoklavsky wafers from the PV industry. And this is one of the second big focus we've done in Nexus, is to rely only on this type of wafers. So all the devices that have been made in this project rely on this type of wafers. Then another topic was also, for example, to reduce rare element like indium, where we have also done some proof of concept devices that use either less or even without indium. So on the perovskite side, as I was saying, working on making high efficiency perovskite top cells, so wide bandgap perovskite, with this either vacuum process or hybrid process, and we have managed to obtain high efficiency with this process, about 20%, which is probably close to world record in this for this kind of process and for these band gaps. And also for some samples, we have demonstrated that it's possible to have devices that can sustain some stability under light and temperature. And then the other focus, as I said, it was to work on Shoklavsky silicon, so industrial wafers from the PV industry. And as you probably know, one of the main challenges of these wafers that you purchase them as cut, so they just undergone a sewing process with diamond wire that leaves a very rough surface that, of course, is already in the normal silicon PV industry etched. And to remove this close to the surface area and make a nice morphology with pyramids to reduce the reflectance of the wafers, which leave like about micrometer size pyramids, which with this vacuum-based perovskite process can work with, because you can obtain a conformal deposition of the perovskite on them. But there are still a lot of, you may have bigger pyramids, or that may cause a problem with the perovskite growth and cause strengths in the top cell. So one of the big works we've done in Nexus was to really address the morphology of these wafers, like to try to etch the surface as smooth as possible, and then grow a texture with smaller pyramids, so sub-micron pyramids, to have a better growth than of the perovskite and get to higher efficiency. So obviously, focusing on these two topics of vacuum-based perovskite and Shoklavsky silicon on the other side, which are kind of two very, not commonly used options in the field. So it took a lot of time to address these two topics and obtain functional devices out of them. And but in the end, after 3 years of the project, we have decent efficiencies with that combine both this vacuum process perovskite and Shoklavsky silicon, with above 27% on a small area, 1 square centimeter. We have brought them to a little larger areas, just above 4 square centimeter, with only little losses. So with this, we can say that we have demonstrated the potential of Nexus approach, so using vacuum process perovskite and Shoklavsky silicon on small scale. Of course, the next step is really to bring it to larger areas. So first, of course, wafer scale area, which you can get as maybe as a demonstrator on this kind of project, but this will cost you a lot of sweat and tears just to to obtain just one wafer because the tools you have right now are just not adapted to it. So really to go to larger area and higher throughput, it is clear that the next step for this is to have adapted tools. And then if you want to see also if they are stable, you first have to put them, to encapsulate them, to make them, of course, so that they can withstand the environment. And so we have also developed bill of material to make modules. It's in industrial bill of material based on commercially available materials, as you can see on the left-hand side, and with an industrial vacuum lamination process. We've managed to make a few proof of concepts for cell mini modules with limited losses in terms of cells to module losses. And we could validate that this bill of materials was able to protect the cells from harsh environments, especially damp heat environments, as you can see with the graphs here. But then, of course, the future challenges of to bring this to even larger scale modules, same as for the cells, and also address the issue maybe of a new cell stability, because of course this is an issue in this kind of collaborative project where you have the cells done somewhere and then made in modules at another place, in which because as you see here, in module we have only get to 20% efficiency despite relatively small losses during the lamination process. But this was because the cells were not high enough in efficiency, and especially the cell that was sent to the partner who was doing the modules. So there's probably not an issue to address here, is how to address the stability of these new cells. Also maybe because for an independent module manufacturer who would buy perovskite silicon tandem cells, how you address this until they are put into and encapsulated and protected from the environment. And then once we had these encapsulated cells or modules, we put them on the roof. We had 3 places where they took the sun during some time in the projects: in Bolzano, in the north of Italy, in Valencia, in Spain, and in Ankara, in Turkey. Not seen here, we had also the facility in Basel, where they were not monitoring the cells in terms of electrical performance, but in terms of lead leaching. So seeing how much lead comes into the rainwater. But here we were just only focusing on the electrical performance. Here we see the results that were obtained in Bolzano with some cells that stayed over a year in all the kind of blue curves. They were benchmarked with a heterojunction silicon cell in black. We've seen, for example, that if you don't have an adapted bill of material with a failing edge sealant, well, your cells really, as you can see here in red, they really degrade very, very fast. So this show really how important is to have a very good encapsulant material for this. And then for the cells that have seen more than 1 year of external environment, for the best of them, it has degraded about 14% in 1 year, which is actually the best you have in the few examples you have in the literature for perovskite and silicon tandems. But it's of course not enough to have a bankable technology. So showing that long-term stability is still something that needs to be focused on. We do have some more recent devices that were maybe installed maybe 6 months ago that seem to show maybe higher stability potential, but of course this has to be monitored for a much longer time. So this is it for this selection of technological results. There are many more that you may find in some of our public deliverables that will be soon published. So what I would like to say is that I think we have demonstrated that there is a potential for high efficiency for this vacuum process perovskite, and also when combining them with this industry relevant Becquerel-based silicon bottom cells. This is really important because it's something which is very rare in the literature, both components, the vacuum process perovskite and the Becquerel silicon. There are some potential for stable devices with an industry relevant module bill of material, but of course we need more results, more study on this topic. But as I was saying in the introduction, Nexus is also paving the way for sustainable technology. So we're doing all these environmental assessments that have actually fed this multi-criteria analysis that Nouha is now going to present. So you will probably get an insight of what has been done on these other topics of the project. And I would like to recall, yes, still on what we have to work. So still demonstrate high efficiency on large area, large scale production. And for this, we need, of course, adaptive tools and still put a strong focus on observing the stability on the long term. And with this, I would like to thank you and give the floor to my colleague Nouha.
Thank you, Perrine. Can you hear me?
Yes.
Thank you. Yes, thank you, Perrine. And we can see you as well, Nouha.
Perfect. Thank you. I will share my screen. I guess this is the one. I started. Can you see my screen now?
Yes, it's perfect.
Okay, so this presentation is really dedicated to the results with focus on sustainability and the results of what is about the sustainability of the Nexus project technology, let's say. So here I will start by presenting the methodology. What was our optimal objective in this project is really to be able, with the assessment to guideline technological choice from the early design process toward the sustainable technology via an eco-design approach, to be able to assess the sustainability of this emerging technology and see where we need to focus in the future in order to be sure that when the technology is ready, we are good from sustainability point of view. So if you have a look at the eco-design approach criteria, this is where we try to focus with the definition of eco-design is to look of multi-criteria analysis, which is economic, social, technical, cost, environmental, etc. So this is what, let's say, what try to do in this project. So the approach is we have the technology development, what Perrine showed before. Then we have this 4 analysis: environmental analysis, the technical analysis, social analysis, and economic analysis. And we try to put them into what we call multi-criteria analysis dimension to establish one eco-efficiency indicator to help us to provide guidelines and recommendation in order for the future development of this technology. So this is the approach, and that's why we had a dedicated work package in the Nexus project, that is the work package 5, who is really focusing on that. So we have a task which is dedicated for the life cycle assessment, the life cycle cost, social impact, circularity by recycling of tandem perovskite, and the challenge of the lead, as was mentioned by Maria. And then we have the final objective, which is try to put all of these criteria together to obtain the main objective, which is the sustainability of the technology via a multi-criteria analysis dimension. So if we have a look at the Nexus results here, I put just some slides, some summary, let's say, but if you are interested, we can have another webinar about the details of this of these results. But here It was work which is done by Iraq, by Becquerel Institute, FNHW for recyclability, and Oxford PV for the cost. So here an example, for example, here of the assessment of the baseline technology compared to optimized one for the life cycle assessment with some details. Here we can see some comparison also always with the baseline compared to optimized for the social impact. Here we have some analysis, sensitivity analysis about the impact of the lifetime on the LCOE, the cost of electricity in euro per megawatt hour. And here the process of recyclability that was developed by the University of FHNW, which allows to handle the lead and the end of life management of this technology. So we got all these results. Now the idea is to gather them to get what we want, which is the eco-efficiency indicators. For that, we develop a methodology which is called MCDA, but it's not innovative. The idea of this methodology is to be able to have one indicator. But if you look at the literature, the problem is for this kind of assessment, we have always, let's say, qualitative analysis, or sometimes we weight indicator, but we don't really, it's not really objective weighting. So we tried here to gather two methodology, one which is the sustainability assessment approach, and then we applied what we call the multi-attribute utility theory methodology. So let's start by the first one. So the idea is to do a state of art to try to analyze what was done from all the criteria, the sustainability criteria. And in order to set our, or to put our technology in front of all these criteria is to define minimum and maximum, and then see our technology. For example, if you have 500 kilograms CO2, we see if it's the 500 is good or not compared to this minimum and maximum, in order to be more realistic. And then once we do that, we try to put a weight for each criteria and aggregate them with a calculator to have the total score. So for that, I will go through the different steps in details. So for that, the first step is to define what we want as sustainability criteria. So what are our criteria? Then we need to score this criteria, or scoring this criteria, so giving like a score for our results. And then we will weight based on the scenario that we want to have the eco-efficiency indicator evaluation. So I will start by the first one, which is the sustainability criteria. How we define the criteria, because if you have a look at the life cycle assessment, for example, we have 17 criteria. Social criteria, we have a lot of criteria. Economic is the same. So we try to do a state of art, to see what is happening today in the state of art, which are the most commonly evaluated criteria in the state of art, and what are our maximum and minimum value that are defined. So what we found, for example, for the environmental criteria, we have basically the carbon footprint, human toxicity, recyclability rate, and resource criticality. For social criteria, I need to mention here that thank you, Becquerel, for the study that you have done, because today we have a few, even I may say, no study about the social impact of emerging technology. So we based our results on the results that was done by Becquerel Institute in the work package. And we define it, let's say, these 4 indicator, which is workers, and each indicator include a lot of sub-indicator. So we have workers, society, local community, value chain actors, for example. For the economic one, we know all that we have the module cost, which is in euro per watt peak, and the electricity cost, which include the lifetime, the degradation rate, or the aspect of durability of the PV module. And for the technical criteria, we have basically the efficiency and the lifetime, which is a key indicator from technical point of view. So now we defined our criteria, let's say, for each category. The next step was the famous state of art. Here, I put just one screenshot, let's say, an example of the state of art that we did. We started from we analyzed all the results, all the publication that studied the silicon tandem perovskite technology. And here, as you can see, each time we identify the lifetime, the carbon footprint, toxicity, if it's mentioned, efficiency, resource use, the cost in other part. And based on that, we were able to identify the highest value, the minimum value, to be able to score our results compared to these results. This is the methodology that I mentioned. So this is the approach. So here, for each indicator, for each value, for example, my carbon footprint is about 500. I will put the maximum that I found in the literature, minimum, and I have a weight. So the weight, I can choose the weight that I want to attribute to the carbon footprint. Then I will have a score. So this is the approach. Once I do that for the different criteria that I listed, I will have my final results or my eco-efficiency indicator. Here, it's a proposition that we done. There is no in the state of art this proposition, but based on what we have from our let's say feedback from working with regulation, with government, etc. about the regulation, we decided to put this sustainability classification. So if the eco-efficiency is more than 50, we can say that the technology is sustainable. If it is less than 25, we can classify it as non-sustainable. And it's between 25 and 50, we can classify it as mostly sustainable. Please note that this value could vary depending on the objective, on the priority, on all the political stuff. So it's not really mandatory to take this value as evidence. Now, this is our methodology that we put and we create really in this project. So then we defined our weight, because here we have a score, but we need to define our weight in order to attribute a weight for each criteria. So we proposed several scenarios, because in order to be objective, in order to have, let's say, to have the overview of all the propositions that we could have, here we propose that, okay, let's say that environmental, we have the same weight for each criteria: environmental, technical, economic, social. So 25 for each one. Then let's say that priority is environmental challenge. So for us, it's priority environmental. The last, we can take it equal. So we put 70 for environmental criteria. Then we have 3. We have 10 for technical, economic, social. The third scenario is technical is critical for us, and the same, we take equal the other indicator. And then we put economic as priority, and the last one, social, as priority. For each one, maybe you may say, what is the carbon footprint? What is the toxicity? They are included in what we call environmental criteria. And here, for example, if I have 4 criteria, I will divide by 4 my 70 or my 25, depending on the criteria that I have behind this category. So we defined our scenario. Please note also that we have, let's say, a tool that we developed in the project that allows to vary and to play with, let's say, with this weight. So it's not final weight, so we can change it, we can put other assumption. But let's say we took that into consideration, and this is the results that we got. So here we have the 5 scenario, and here we have the baseline and the optimized. So maybe I just need to define what was the optimized solution. The optimized solution here was that we produce in Europe. We optimize the technology, the Nexus technology, we increase the efficiency, we try to do our best, to optimize the best technology that we want as sustainable. So here, as we can see, if you look at the baseline results we can have compared, we can see that almost for this scenario, we are mostly sustainable. We can see for scenario 4, we are not sustainable. And for the scenario 2, where here the technology is sustainable. But for the optimized, results prove that really the technology of Nexus project is really good and could be sustainable, even though the challenge of durability, the challenge of the cost. And here we can see, for example, the challenge of the cost, where we are mostly sustainable. Sorry, maybe I have a mistake here. It's more 23 or 40. It's mostly sustainable. And then we have the sustainability here if we have the priority of social, priority of environmental, and priority of technical. So these results show that maybe when we remove the technology today the technology as was developed in Nexus project, taken into account all the challenge of criticality, of recyclability, of carbon footprint. We are a technical also challenge. We are able to prove that the technology is sustainable. Still, maybe the big challenge could be the cost of the technology, which is normal, and we are all, I think, aware about this challenge in Europe, but could be maybe handled by regulation, by, as was mentioned before, by the Net Zero Industry Act, by the non-price criteria that could help manufacturers to be able to settle in Europe and to produce technology in Europe. Because in Europe, you have all, let's say, all the benefits to have a sustainable technology, either from carbon footprint due to the electricity mix of the country, from recyclability, because let's say today we are developing a tool, developing a process which are really, really important for the PV field today, to be sure that the technology will be management by the end of life, and also for social aspects like labor force, like parity between women and men, like all these challenge workers, local community, etc., that we can, let's say, check it due to the European production. So here I just put like maybe a future, if we want to guideline, because the objective of this analysis is to see, are we good or not? Should we continue to work on perovskite tandem silicon or not? Or so maybe this question. So maybe the results prove that we are good. We can continue to work on that. Some challenge from cost point of view, maybe technical point of view, but I think that technical is the big challenge for all of manufacture today. All people are working on to improve the technical aspect. But at least in Europe, you are sure that our technology is sustainable, is really with the lowest environmental impact and recyclable by the end of life. So maybe here some guidelines. So for me, maybe it's mandatory, maybe since the technology is, we are talking now about emerging technologies. So we are looking for data, we are looking for a methodology in order to be able, all people do the same assessment of life cycle assessment, of life cycle, of social impact, of economic analysis. So maybe it is worthy to start working today on establishing a guideline, or maybe a common methodology to be able to guide technological choice and be sure that all people are using the same methodology. Because here we do a life cycle assessment, choosing methodology that is recommended by Europe. Maybe in other projects, people are using other methodology, the results will be not the same. So the technology, the decision making will be hard in that case. So I think that eco-design approach is establishing a common eco-design approach or a common methodology of life cycle assessment is mandatory today for this emerging technology. Also, circular economy incentive. So today we saw that the challenge for producing perovskite is basically the cost, but let's say for maybe we can help by enhancing or incentive for recycling, since we do it today in Europe, in other countries still not mature. So maybe we could encourage that in order to compensate the cost and the challenge of cost that we have, for example, at the manufacturing stage. Also to encourage local and local and production in Europe, and I think it was really start to be done by the Net Zero Industry Act, and there is the non-price criteria that will be in the call of tender in January 2026. And the last one is the definition of measurable performance indicators like recycling rate, like carbon footprint, certified chain, that encourage manufacturers to do their best and to have the same methodology, and to be sure that if you don't do it, you can get a malus. You cannot be able to install in Europe, in Italy, in France, in wherever. So it will enhance them to do that, and we will be sure that all the PV that we have and we install in Europe is sustainable, and we could handle its end of life. And we are sure that we are talking about clean technology in the field. So thank you for your attention, and happy to answer questions.
Thank you, Nouha. If you could stop sharing, that way we can see both yourself and Perrine and Maria and our audience. If you have questions, please, we're not too many of us, so you can put your hand up or use the chat to ask any questions. I'd like to ask a question to start it off. I just checked, we've got 6 minutes left, is that right, Perrine? Okay. One very quick question, Nouha. Maria said in the beginning, one of the things that the Commission is really keen to see happening is cross-project collaboration, where maybe different groups of researchers focalize on one part that's complementary to the others. And you've said one of the things that would be really good in terms of for policy, in terms of reaching the sustainable goals, is having shared guidelines in analysis and assessment. They're not quite talking about the same thing. How do we reconcile this? Or is it the basis of collaborative work is having a shared language and shared guidelines?
I don't know, Maria, if you want to start or I can start.
Please do so. I will complement afterwards.
Okay, yeah.
Complement, I'm sorry. I mean, I will tell you what we are planning for the next topics.
Oh, perfect, great. Yeah, it's a good question, Melodie, but my point here is today we are doing assessment of sustainability from the early design process, which was not the case 10 years before. So I'm really happy when I see that we are doing that. But the problem is we can do everything, and everybody can justify his methodology. So today we can do at least carbon footprint, for example. It could be able to be assessed several ways, and you can have for the same product or the same module several results. So for me, in order to be sure that what we put in Europe, what will be installed in Europe is really sustainable or is really good, we need to have the same methodology at first to assess the sustainability. After, let's start doing research, R&D, development, etc., eco-design, etc. But at least we need to harmonize and to have this harmonization between at least the European member to have this unique methodology of assessment. So for me, it's mandatory today.
Thank you, Maria.
Yes. So thank you very much for your presentation, which was very, very good. But also for the point that you raised. And actually, there has been an acknowledgement for this necessity across many technologies, not only on perovskite, for which also data are lacking because we don't have enough data on this. But in the next in the next work program, we actually have an administrative agreement with JRC, and JRC will be requested to develop a unified methodology, a life cycle assessment methodology for all PV categories, and a social life cycle assessment methodology, but unified. So they will provide the prototype, the unified methodology, which can then be implemented for the various categories of technologies. So for perovskites, for silicon, and of course, the respective databases need to be there.
Yeah.
So which is another important part of the story. It's not only the methodology, but that we are using the right data. So this from that part, but my, what I said previously is that because we are in a competition, we are in a race, let's say, to put forward which of the technologies which will come first in putting into the market a tandem perovskite, silicon perovskite, or even simple perovskite technology, it is important that we collaborate because, okay, in Europe, we are many countries, many institutions. Thankfully, according to me, there is the European Commission which funds projects among the various countries and among all institutions. So there is already a collaboration, but I think we should go even farther, join forces, as I said before, and share information in specific parts or specific challenges that perovskite face. So collaboration, for example, in architecture, breakthrough architectures, or interface engineering, or material innovation, or lifetime and stability for perovskite. So thematically working together is something that I believe would be important. And by joining forces in certain aspects, and first of all, technological aspects, would be important so that we can actually go farther than the state of the art in these areas, in these aspects.
And do you have an idea how this could be implemented in practically?
Yes, saying this is simple, but how you do implement it is harder. So we have the ETIP, for example, and the partnership from our side. From the European Commission side, we have set up a partnership, a co-programmed partnership in photovoltaics in order to identify which are the industrial challenges, let's say, or in order to connect more with industry and provide support in those areas that can increase this competitive advantage, not only in perovskite, but perhaps in other areas of PV. So if, for example, consortia prepare themselves beforehand and before a specific topic is launched, but if they join forces in an area, okay, in perovskite PV, and they also specialize or make links, or they divide their forces, but under areas, then we can respond to that need under this partnership and say, okay, we can launch a topic in that area for which the consortia or the institutes are already prepared in order to respond. Then in another area for which other consortia are ready to respond, etc., etc. It doesn't mean that we are going to top-down indicate what you are going to do. There must be a form of self-organization, in a sense that you are going to organize yourselves, and then we can respond in terms of financing in the areas that have been identified and in the collaboration areas that have been identified by you.
Mm-hmm. Could we say that Nexus as one of the few projects that's looking at non-solvent-based deposition with a collaboration across the European research community is already kind of an illustration of that, of where the Nexus partners weren't specifically competing with other research groups because there's not that many actually working on this, and there was a conscious decision to bring those that are already looking at that subject together. Were we kind of heading in the right direction already with Nexus when we were doing that?
Yes, I think so. I mean, it is under the, if I group the challenges of perovskites, there are environmental challenges, let's say. And then you are tackling the environmental challenges. At the same time, you are tackling the scalability challenges, because this combines two challenges at the same time. So yes, indeed, it is an example of tackling, as I said, these challenges. If I may so, you know much better the project than myself. So yeah. But it is important that in that specific area, you join forces. And then by joining forces in an area, perhaps we can go farther, faster.
Perfect.
I don't know if I have answered
Yeah.
your question, but
it was really good and encouraging for us to continue to work on this topic.
Thank you. Thank you.
Thank you, Maria. Thank you, Nouha. Thank you, Perrine. Thank you to our audience. I see our project partners and our network, PEROVSKITE network, which is something we've been very active in the last 2 years, encouraging all these different Horizon European projects to work together, which I think it's also one of the successes that Nexus can be happy with, because all these partners were very keen to co-organize webinars and workshops together. And I think we have really worked on that, accelerating the information sharing and the dissemination within the European perovskite community. So we're very pleased with that. If anyone else has any questions, and I just checked I didn't see anything in the chat, you can raise your hand. Perrine, Nouha, myself, we will remain available. You have contact details, I think, in the webinar invitation. Do not hesitate to get back in contact with us if anyone has any questions. We did record the presentation, and I think it could be interesting to disseminate it a little bit more widely, because it's true that we address some subjects which are not easy ones, and I think there's a real interest in the research community for these. So I'd like to thank everyone for joining us. If anyone has any last words, I'm happy to hand over.
Thank you, Melo.
Thank you, Melodie.
Thank you, Melodie and Camille, for organizing this. Thank you, Maria, for joining.
We're very keen to hear your feedback, Maria, and your perspectives on what's coming up in future calls, and how we as Research Consortium need to work together to adapt to what Europe really is want to have.
You're welcome, and thank you all for this organization, for the organization of this webinar.
Thank you very much, and we wish you all a very good late lunch if you haven't had lunch yet.
Bye-bye.